Hey guys, so we're going to go ahead and talk about the existence of the derivative. So it is possible that a derivative might not exist at a particular point. So here a couple of notes that I've written down are that not all functions are differentiable. And so we need to keep that in mind, that just because we have a function, it doesn't necessarily mean that it is differentiable. You may be able to find the derivative of a function, but it doesn't mean that the derivative will exist at every point that you can think of. There might be some points within that function where the derivative might not even exist, and we'll talk about that in just a moment. So differentiability, I need you to think about that as a smoothness condition of the graph. And so the graph needs to be smooth at around a certain point in order for the derivative to exist. And so what I mean by that is we have three cases. So case number one is if the graph has like a corner or a cusp. A cusp and corner are kind of the same thing. So imagine that we have a function that looks kind of like this. So it goes up and then it, kind of dies down. Well, the derivative at this point, let's call this point right here, let's call this C. The derivative at C is not going to exist because, again, there is no smoothness here. Remember, the derivative is the slope of a tangent line, and so think about trying to draw a tangent line here. It would be kind of difficult to do that. In fact, you might say, well, look, here's a tangent line. It kind of scraped the graph. It kind of only touched at that point. But then somebody else could say, look, there's another tangent line that we could draw that kind of scrapes the same point. And so it's kind of difficult to just have a single tangent line at a corner or a cusp, because you can kind of draw any type of line scraping that corner once. And so that's an example of where the derivative would not exist. Case number two would be like a vertical tangent. So again, let's say that we have a graph that kind of does something like this. Kind of shoots up, and then again we have another part of the graph that kind of comes back down. But at this point, let's call this a vertical asymptote. We'll call that C. So at C, notice that this graph doesn't even exist, so therefore the derivative would not exist there either. And then finally, the other type of case, or case number three, is a discontinuity. So let's say that we have a graph that does something like this, and then here we have, a hole or a gap, and then again the graph kind of continues doing its own thing. Well, let's say that this point is, again, C. Well, we could say, look, at C, there's no way we can have a tangent line at some gap, and so the derivative there would be would not exist. It's non-existent. So these are the three cases where a derivative can possibly, not exist. And if I just go through some notes here really quick, the previous video, the previous example we did, we calculated the derivative here. And I said earlier that, look, the derivative of this guy is not going to exist when x is equal to 0. When x is equal to 0, we're going to end up dividing by 0, and that's going to cause some issues. So that means that the derivative is undefined there. It does not exist. Also, x cannot be negative, right? So x cannot be negative. If x is less than 0, then you're going to have some imaginary solutions here, some imaginary values that are not going to really make sense when we're talking about the slope of a tangent line. So there are some restrictions when dealing with the derivative there. Now let's talk about something really important involving the existence of a derivative and then also continuity. So how is differentiation and continuity, how are they related? And if you haven't maybe thought about it by now, hopefully this has popped into your head sometime throughout the lesson or sometime throughout the video. But this is really, really important to understand that if a function is differentiable at a point, then it must also be continuous at that point, because differentiability requires the function to be smooth and continuous. So if the function is differentiable, then it must also be continuous. And again, we are talking about a specific point, not the entire function in general. However, it does not work the other way around. So if a function is continuous at a point, it does not mean that it is differentiable at that point. And an example of that would be case number one. So if I pull back up case number one, notice that this function was this function was continuous everywhere, right? It's even continuous at C. There was no hole or gap at C, but it was not differentiable at C. And so that's kind of what this is saying, is that just because a function is continuous does not mean that it is differentiable. However, if we go backwards, if it is differentiable, then it must also be continuous, because that is a requirement. All right, so this could be a little confusing at times, but one way to think about it is with this kind of picture that I've seen drawn before. But imagine we have, a set of functions. So this is like all the functions that you can possibly think of that are continuous. Okay, so these are all the continuous functions that you could possibly think of. Maybe you know a few, maybe you don't know them all, that's fine. But let's just say that that is a world right there of continuous functions. And within this world, we have a separate world, and in this separate world are all the differentiable functions. I don't even know if I'm spelling this right. Differentiable. I think there's an I in there somewhere. I don't know, but these are all the differentiable functions. And the way we read this chart or this little drawing is that all the differentiable functions are continuous, right? But all the continuous functions are not necessarily differentiable. Some are, but not all of them, right? So everything that's in here, everything that's differentiable is going to be continuous. However, but everything that's continuous, I'm getting confused myself by just saying this over and over again. Everything that is continuous doesn't necessarily mean that it's in here as well, because we could have a function sitting out here, like for example, here's a good one, y equals the square, I'm sorry, not the square root, but the absolute value, oh yeah, maybe even the square root, the absolute value of x. Now think about the absolute value of x. The absolute value of x looks like this. So there's the y and the x-axis, and again, here's the absolute value of x graph. It's continuous, but is it differentiable? Well, it's differentiable maybe here, right, and here, but it is not differentiable at 0 because we have that corner happening, that cusp. So again, it's a continuous function, but it doesn't fit quite in here. But think about, let's say y equals, I don't know, x squared. Well, x squared is a continuous function, and it's also differentiable, so it fits both categories. So hopefully this makes sense to you. If not, just play around with the idea. Pay attention to when you're finding derivatives, and just look and see. Maybe try graphing some of these functions. Like, try graphing the derivative function and see what it actually looks like, and see if any of these cases pop up on that graph. And that might be a good way to kind of drive the nail home, or drive the point home that not all continuous functions are differentiable, but definitely differentiable functions are continuous.